Alright, let's get started here with section 5.5, the real zeros of a polynomial function. So, there we go. Alright, so the first thing we're going to do is use the remainder and factor theorems. So, if you think about a rational function, f of x over g of x, as being able to be broken down into two pieces, the part without the remainder and then the part with the remainder, we're going to call those parts q of x and r of x. Alright? So r of x is either the zero polynomial or it's the polynomial of degree less than g of x. So obviously you've got to have a smaller degree in the numerator than in the denominator. Alright, so we can use that to go back to what we learned about synthetic division to say if you have a polynomial f, alright, if you divide it by x minus c, then the remainder is f of c. Alright, so if there's a remainder, that's the value if you plug in c. So let's figure this out here. So x plus 2 is what we're dividing into x cubed plus 3x squared plus 2x minus 1. Let's do some synthetic division. Negative 2, 1, 3, 2, and negative 1. Bring down the 1. That'll turn into a 1, negative 2, and 0. And then we'll have 0 here. And so we'll have negative 1. And so what we have here is we have a remainder of negative 1. But we can also say that f of negative 2, if we take negative 2 and plug it in for x in all of these places, the answer is going to be negative 1, whatever the remainder is. Alright, we can do that also here with x minus 1, so the 0 is 1. Let's go with our coefficients again, 1, 3, 2, and negative 1. Bring down the 1. 1 times 1 is 1, 4, 6, and then 5. So, f of 1 is 5, since the remainder is 5. Alright, so let f be a polynomial function, then x minus c is a factor if and only if there's no remainder, because it's a factor if we cross at 0, right? And so we need to have a y value of 0, which is what we were getting from synthetic division. Alright, if x minus c is a factor of f of x, then f of c equals 0. Going in reverse, if f of c equals 0, then x minus c is a factor. Okay, let's use the factor theorem to determine whether the function has the factor x plus 1. So again, we'll use our synthetic division. Negative 1 is the 0. Negative 2, negative 1, 4, and 3. Negative 2 times negative 1 is positive 2. That's a 1, a negative 1, a 3, and a negative 3, a 0. So yes, it does. It factors into x plus 1, negative 2x squared, plus x plus 3. Let's see if x minus 1 is a factor, so we would use 1. Same coefficients, negative 2, negative 1, 4, and 3. So we would have negative 3 here, which is a 1, and that's a 1, and so we'd end up with a 4 there, so it is not a factor in this case. Alright, why don't you try problem 11, see if you can do these type of problems. Alright, a polynomial function of degree n, n is greater than 1, has at most n real zeros. So if you are x to the 5th, the most zeros you can have is 5. Alright, so we're going to use that a lot here. Use the rational zeros theorem to list the potential rational zeros of a polynomial function. So, you can write this whole thing down here if you like, but here's what we're saying. Possible zeros. You're going to take the factors of the trailing, the final constant at the end, divided by all the factors of the leading coefficient. So, this is p, and that's q. Alright, where you see here q is a of n, and p is all the factors of a0. This, I think, might make more sense with an example. So let's take a look here. What are all the potential zeros? Not the actual zeros, but things that could be zeros of this function. So we're going to take the 12. We're going to write down all the factors of 12. So 12 factors to 1, 2, 3, 4, 6, and 12. right? 1 times 12, 2 times 6, 3 times 4. 3 is just 1 and 3. 1 times 3. So what are all the possible zeros? Plus or minus. And here we go. 1 divided by 1 is 1. 2 divided by 1. 3 divided by 1. 4 divided by 1. 6 divided by 1. And 12 divided by 1. And then all of these divided by 3. So 1/3, 2/3. 3/3 is the same as 1, so we already have that. 4/3. 6/3 is the same as 2, and 12/3 is the same as 4. So those are all of the possible rational zeros. See if you can find the possible rational zeros on problem 21. Alright, third objective. Find the real zeros of a polynomial function. So, 4 steps here. We're going to go through all 4 of them. Step 1, use the degree of the polynomial to determine the maximum number of zeros. Alright, so we've got x to the third, so 3 possible zeros. 3 places where we might cross the x-axis. Step 2, if the polynomial has integer coefficients, and it does, those are all integers, use the rational zeros theorem to identify those rational numbers that potentially can be zeros. So let's go find our possible zeros. So this is 12 factors of 12. 1, 2, 3, 4, 6, and 12 over 1 and 3. So we just did this. So this was plus or minus 1, 2, 3, 4, 6, 12, 1/3, 2/3, and 4/3. You can look back on the last problem if you need to, but those are the possibles. Alright, step 3. Use a graphing utility, graph the polynomial function. So we're going to bring up this graph, plug it in to the graphing calculator, and see what we get. So I've already plugged this in. So this is graph 1 here. 3x cubed plus 8x squared minus 7x minus 12. That's in there. And so I'm going to go ahead and graph this, and let's take a look at some possibles. Okay, it looks like now -3 looks like it works, right? We could zoom in and get closer, but it looks like -3 is a 0 here. So we're going to use the factor theorem to determine if it actually works. Use synthetic division to factor out. Alright, so we're guessing that -3 is a 0. We're going to do some synthetic here. 3, 8, -7, and -12. If it works, we're going to get a 0 down here. So let's see if we do. -9, that's a -1. That's a 3, a -4, a +12. Hey, look at that. All right, we are factored. So right now, we have factored down to x plus 3 and 3x squared minus x minus 4. All right. Now we could go back into our graphing calculator and do this again, but once we get to the x squared stage, let's try to factor if we can, see if it'll work out for us. So 3 times -4 is -12. We added -1. That's going to be -4 and 3 over a. So there we go. This will be a 1 and a 1. So we've got x plus 3, 3x minus 4 from here, and x plus 1. Alright, and we are completely factored, so the rational zeros would be -3, -1, and 4/3. Okay, so here once again are those 4 steps. If you want to, you can pause the video and get those down. Okay, let's do this one more time, finding the real zeros. So we've got a lot of options here. 4 possible zeros, and the possibles are going to be the factors of 9, which is 1, 3, and 9, over the factors of 2, which is 1 and 2. So possibles are plus or minus 1, 3, 9, 1/2, 1.5, 3/2, and 9/2, 4.5. Let's go to the graphing calculator, take a peek at what this looks like. So I've already punched this in as well. Let me turn off the first one, turn on this second one, and let's go ahead and graph it. And what do we see? Something's going on in here. It looks like -3 again. So let's give -3 a shot. And so we've got a 2, a 13, a 29, a 27, and a 9. -6, 7, -21, 8, negative 24, 3. All right, our guess worked out. Okay, but now we've got 2x cubed. We're not at x squared yet, so we're not ready to factor. So let's go back to our graph and grab one more. Now, really tough to see what's going on in here, so I'm going to do a box zoom. Get a little closer in there so we can really see what's going on. So there's your negative 3. Okay, looks like negative 1 might be a multiple 0. So let's try negative 1 here. Now, since we factored it, we can do it just on the factored piece, the 2, the 7, the 8, and the 3, because we're trying to break this down. And let's see, did I make a mistake here? There it is. 2 times 1 is 2, so this is a 5. And this is a 3. This does work out. And we thought it was a double 0, so let's try negative 1 again. 2, 5, and 3. And it does work out again, and so we're factored all the way down here. We've got x plus 3. X plus 1 squared. And then we have 2x plus 3. And we are completely factored. All right, try problem 39. Okay, objective 4, let's solve polynomial equations. So, if we have an equation, we have to set it equal to 0, and then we need to find all of the x's. So we're going to do the exact same thing that we did in this problem. It's the same equation, actually. And so we know if we followed the same steps through, we would end up with x plus 3, x plus 1 squared, 2x plus 3 equals 0. So, of course, x equals negative 3, negative 1, and negative 3 halves. Alright, so every polynomial with real coefficients can be uniquely factored into a product of linear factors and or irreducible quadratic factors. So what this is saying is you can always take a bigger problem and break it down into your smaller parentheses. Alright, a polynomial function with real coefficients of odd degree has at least one real 0. So what we're going to jump in here, and we'll talk about this more in 5, 6, but you can always break things down into the parentheses if we have real coefficients. Alright, last thing we're going to do here is we're going to do the theorem for bounds on zeros. So here's what this is. When you have a problem that you want to put in your graphing calculator, what do we do when we say, I wonder what the x min and x max should be to make sure we see everything? That's the bounds. And so we have a formula that will tell us. So here's what we're going to do. Now you have to have 1 for your leading coefficient. After that, we're going to ignore the first term and use all the rest of the coefficients in these two formulas. Alright, so max means in this list, take the bigger of them. So 1 versus, add up all your coefficients and the absolute value of them. Compare them, take the bigger one. Versus 1 plus the biggest coefficient, absolute value. The bounds are going to be the smaller of those two numbers. Alright, so let's try some examples here, see if that makes sense. So, in problem A, we have a 1 here, so we're going to ignore that for the time being. We're going to use 3, 9, and 5. Remember that we're just using the absolute value, so we don't care about the negative. Alright, so we're going to say, what's the max between 1 and, let's add these up, 3 plus 9 plus 5. 3 plus 9 plus 5 is 12, 17, so the maximum between 1 and 17 is 17. Alright, and then 1 plus the maximum number in your list of 3 or 9 or 5. So the maximum number in your list is 9. So what's 1 plus 9? 10. Alright, so which of one of these two is smaller? 10. So we know that all of the zeros have to occur between negative 10 and 10. Those are the bounds for that polynomial. Alright, let's try B. Problem here is that we don't have a 1. So we need to pull it out. So we're going to say 1/4, and then we'll have x to the 5th minus 2 over 4 is a half, x cubed plus a half x squared plus a quarter. Alright, so we're going to use a half, and a quarter and add them up. So between 1 and a half, and a quarter, that's 1 1/4. Which one's bigger? And then we're going to say 1 plus the biggest number on your list, which is a half. Which of those is smaller? 1.25. So now we know that the bounds for the zeros of this polynomial lie between negative and positive 1.25. Okay, so now we can use that to graph these. So same thing, we know that this is in between negative 10 and 10. That's where all the zeros happen. This is between negative 1 1/4 and positive 1 1/4. So, obtain the graph. We can go to our graphing calculator, and let me turn this third graph on. And now I know my window is going to be between negative 10 and 10, which just happens to be our standard view. And let me change these y's to something a little nicer. How about negative 10 and 10 again? And we can go ahead and graph. We know that we have a maximum of 4 zeros. We have 1, 2, 3 in this case. I'm sorry, maximum of 5 zeros. So we have 3 in this case, but then it's going up and down forever. We know that it never turns around again because negative 10 and 10 are the biggest zeros we could have. Consequently, if we look at the other graph, turn that one on, I know my windows have to be between negative 1.25. So let me say negative 1.5, so a little bit smaller and a little bit bigger. I'll be guaranteed to see all of the zeros. There's 1, and we don't have any more. Just 1 real 0 for this polynomial. Don't have to search for the other 4. Alright, problem 33 is yours to try. And then lastly, we have find the real zeros of the polynomial function x to the 5th minus 1.8. Okay, these are not integers anymore. So if we don't have integers, we have to go to the graphing calculator. But we still could figure out what the bounds are. So on this one, what are our bounds? If we added all those numbers up, and I've done that already, so you don't have to. If we add them all up, we get, where do I have it here? 97.9241. 0.9241. Now, compare that to 1, and obviously this is the maximum. And then 1 plus, what's the biggest number on the list? 37.95. So we get 38.95. So where are our bounds? Our bounds are going to be between negative 38.95 and 38.95. Alright, so let's go to the graphing calculator. Turn it on. I know my window is going to fall between negative, let's go with negative 40 and 40. And there we go. I'm guaranteed to see everything in there. Looks like everything's happening right in this region. I'll do a box zoom. Around those important points. Alright, and then what we would do on this, because we're not going to do synthetic on the decimal problems, I would use my solving, my calculate feature, and I would get negative 4 here, negative 1, I'd have to zoom in here, there's another 0 here. Look at this, this is steep, it almost comes down and turns around and goes back up. So this is a very narrow graph, but I would have 1, 2, 3 real zeros, and then the other 2 are going to be imaginary, which we will talk about in 5, 6. Try problem 57 and you are done. Alright, good luck with those problems. We will talk about any questions you have in class.